Okay, thank you so much for the introduction, and thank you everyone for being here for the talk, and especially to the organizer for making it possible for me to participate remotely and give this talk. I unfortunately had a personal issue. I had to cancel the trip just a few days ago. So it's my great pleasure to have this opportunity to present work that my group did in the last 10 years in a simulation with contact. And what I'm going to discuss today is an approach for doing large-scale nonlinear elastic simulations with contact, with friction. And the main focus of this talk, which I think is going to be complementary to many of the other presentations in this workshop, is on implementing algorithms that are very, very reliable. So for example, in this simulation, there are going to be around 500,000 contact pairs to solve at every frame, and the algorithm can very reliably solve them, especially in this situation where there is a lot of cell contact and complex geometric configurations. So the main goal, and that's why I feel like it's going to be quite a different talk with quite a different set of techniques, is preventing catastrophic failures. And just by recall what a catastrophic failure is a failure of a system which recovers meaning that usually it requires the user to fix them. Right? And if you think about it, in most of engineering, the main goal is to design systems that do not catastrophically fail. For example, if you're designing a car, you're going to do your best to not have flat tires. And if it does happen, that's something that needs to be fixed by users, like expert users. In my case, I will not be able to do it myself. So one thing that is sort of annoyed me for quite a while is that in numerical codes, but especially in numerical code that involves contact, catastrophic failures are very, very common. There is usually a lot of needs for modifying the geometry, tuning parameters, and so on. And so the question is why, and is it possible to try to design algorithms that do not catastrophically fail provably? And there are many reasons for this. And one of them, which I think it's rarely discussed, but I think it's an important one, is that it's very natural to develop methods, prove some results using real numbers. Unfortunately, when we end up implementing numerical methods, we cannot use real numbers, or technically we can, but it's going to be computationally unfeasible, way too slow. So we usually switch to floating point. The challenge there is that when you do this switch, there are many properties of real numbers that do not apply anymore. And just some of them, just to make sure we are all on the same page, is that multiplication does not distribute over addition anymore. If you have a function implemented in floating point, the gradient that you can compute in general might not be an ascend direction. Right? There could be numerical rounding errors, and this could actually make it point the other way. More crucial for intersection, for contact, some geometric queries, like you take two segments, just making sure. Do you see the annotation on my screen? No. Okay, I'm going to annotate. I'm just going to show it with hands. So if you have two segments and these two segments intersect somewhere, in general, the point of intersection, if you compute it in floating point, will not be belonging to any of the two lines. It's going to be close by, but it's not going to be on the lines. And so usually the approach to all of these is to not care about it, which leads to algorithms that usually work, but sometimes don't. And what is going to be different about this talk is that in this talk, whenever I say that I guarantee something or we have a property, I mean it also accounting for floating point rounding. And so a lot of the differences in this talk compared to other methods for handling contact is that everything is designed in such a way that it's possible to prove correctness in floating point. And that's why some of the choices are kind of awkward and suboptimal, but they allow proceeding this way. So if you have questions, feel free to stop me anytime. I'm really happy to take questions and answer at any time. So what I want to do for the talk is spend 10 minutes or so to talk about why I care about robustness and what kind of problems I would like to solve. You see that I mostly publish in graphics, but many of the applications are actually in biomechanics and in mechanical engineering. And then I'm going to give a brief overview of the approach itself. So what I'm trying to do is to solve very large-scale deformations where contact surfaces are not specified a priori. They are just derived from geometry. This is 2.5 million elements, around 100,000 contact per step. And in here, there is a guarantee that every frame in this simulation is going to be intersection-free. Of course, I'm playing things in real time here. These are absolutely not real time. This takes like hours to day to run each one of these sequences. This is an example of a thin sheet meshed with one layer of tetrahedra, and then we're going to, on purpose, bend it around and then fold it. And as you can see here, of course, there is like a lot of distortion, but there are interesting effects that are appearing in the middle due to this sheet bending and twisting. Here is another example, just to clarify that all the examples that you see do have friction. Here is an example of a rod which is moved horizontally on a plane, and the part in the bottom is touching the ground, and there is a stick-slips behavior where you transition from static friction to dynamic friction. This is an example that it's very good because it's the one that we use to sort of show robustness. So this is an example where if you try existing simulator with contact, you can usually break them by adding more and more chains. At some points, all codes eventually break, with exception of what I'm going to describe today, which by construction cannot break. But the downside is that the more chains links you had, the slower the method will be. It's going to take longer and longer and longer the more links you have. So one guarantee is no intersection no matter what. So the initial state has to be intersection-free. The final state is probably intersection-free. And not only this, but also the entire trajectory in solution space over time is guaranteed to be intersection-free. The second invariant, which is not directly related to contact, but it's important, is that every element will have a positive volume. Or if you want, the interior of every element, doesn't matter if it's linear or high order, has positive Jacobian everywhere in its interior. So this is really crucial to get these simulations to be robust. And I think it's something that might be interesting, especially for methods that use a third medium contact, because there usually you use positivity of volumes as a sort of replacement for contact constraints. What you can do with this, so if you have a simulator that it's so reliable, then you can start to simulate things like this medical implant. This is a medical implant to support tissues after surgery. This is a collaboration with a medical school in Pittsburgh. Here is a simulation where every one of these rods is actually volumetrically meshed with a tetrahedral mesh, and then the interesting behavior that you see here appears purely through contact between the fibers. And what is exciting is that in such a setting, we can embed some solid in there. In this case, is simulating the human tissue where this implant will be installed. And then you can see how the deformation of the implant affects the tissue and also the other way around. And so this approach, while extremely slow, like one of these sequences takes around a week of simulation time to run, it's what is currently being used to by the group at the medical school to design and decide what material should be used for the implant and how should be knit together, because this has a huge impact in the material properties of the implant. This is another example that actually appeared in some similar form in a previous talk. I don't remember who gave the talk, but would love to connect later on. So this is a small sample of the optical nerve of a pig. And the reason for looking at this is a collaboration with Ian Seagal, also University of Pittsburgh, where their goal is to understand why some of us, as we age, lose our sight faster than others. and there is a belief that there is potential mechanical damage in the optical nerve, right? I mean, the optical nerve is moving in our skull for our whole life, and it's possible that different geometries might affect and provide damage as we age. And so one of the questions is, how do you model this material, which is like a massive network of fibers? And as far as we're discussing with Ian, and he has a few papers on this, it's very hard to have bulk models for this. And the only simulator that where it could get some good agreement is the system that we developed, which he used in a very interesting way. So here, this is what you see here is scan done with a micro CT of an actual sample of an optical nerve of a pig, which has been acquired with a micro CT and then tested mechanically with a mechanical testing machine with a column. And then here you see the simulation, which is done by extracting individual fibers from this micro CT, meshing each one of them as a volumetric mesh, and using our simulator to solve the same stretching experiments. And what it turns out is that the errors are around 20 to 30% on displacement, which for the complexity of this is pretty insane. And the curious observation here is that the material model that you use is not so important. So most of the interesting material behavior here really appears from the contact and friction interaction between the fibers, which was kind of like unexpected. Again, like in a case like this, you have millions of contacts per frame. So whatever algorithm you use here needs to be extremely reliable if you want to hope to make it to the end of such a simulation. Another one, this is a collaboration with Pittsburgh and the University of Columbia here in New York. This is another project where images from ultrasound are used to simulate, customize for specific patients, human birth, for the goal of deciding if it's possible, if a surgery is required, or if natural birth is the preferred option. So this is another ongoing project where the automation enabled by this method will hopefully lead to something that is usable in a clinical setting. So I hope that I convinced you that there are a lot of interesting problems, especially on biomechanics side, where complex contact with complex geometry, it's interesting. But the reason I started looking into this 10 years ago was really for working on inverse problems. So just to clarify what I mean is classical forward simulation. You have a domain, you have boundary condition, you're trying to compute, in this case, stresses that are derived from displacement. But an interesting question could be, can we maximize the strength, minimize the maximum stress in here by modifying the shape? And of course, there is contact involved. You see that these are separate pieces which interact through contact. And if the formulation is differentiable, and everything I'm going to present today is differentiable, actually allows you to use shape optimization. So in this case, you get this more organic looking assembly, which has considerably lower stress than what we started from, where unsurprisingly, all the sharp corners disappear and they get smoothed out, but in an optimal way. This differentiability is done in an efficient way using an adjoint method, so it can be applied to very large scenes. The sort of rule of thumb is that if we can forward simulate, we can also optimize it. This is an example of an optimization in 3D. And going forward, we can use these techniques, for example, to optimize for geometric metamaterial families. These are geometries that are realized in a single material, but by changing the geometry of the object, you can get different bulk properties. And so, for example, the reason why this requires a lot of automation is because we need to run millions of simulations to find and test all of these different geometries. The sort of outcome is that we can do things like this one here, where we see that it's a single piece of material. You compress it on one side, it does compress also on the other side. And this geometry is completely automatically synthesized by our algorithm. And the trick is that the algorithm is going to place some tiles in here that have negative Poisson ratio. And so this creates some sort of mechanism. We have extension of this to 3D. But one more recent work that I would like to mention that I'm excited about is that we can now optimize microstructure families also with nonlinear materials and keeping contact into account. In this example here, we're trying to design a foam to protect this object, this duck. And after optimization, we get a new geometry for a foam where for this specific scene has a much, much lower maximum stress, reduced by 72%. So what is exciting here is that we can actually optimize over time. So we can minimize max stress over a time sequence. And as part and visual simulation, there is nonlinear elasticity, contact, and friction. In this paper, the sort of key result, and it's something that we experimentally validated, is that we discovered a new family of periodic metamaterials which are ideal shock absorber up to 60% strain. So here is an example. In orange is what our simulator predicts. In blue is the actual measurements. And you see that we have materials where until 60%, a little bit less in this case here, we have perfectly linear response, right? That's the optimal thing that you can do, because if you have an object falling down, it's going to minimize the stress on the object that you're trying to protect. So in general, we are trying to do extensive physical validation for all the projects that we have, and I'm just going to refer to the individual papers if you're more curious about how we validate. As you can see here, this is a simulation that involves nonlinear elasticity and contact, and we are maybe with a 10-15% error compared to experiments, which I believe it's pretty good, given how complicated this is and how crude our fabrication procedure is. More project of other people using this code. We have a collaboration with the medical school at NYU where we are using this method to optimize the shape of bones during surgery so that they can figure out how to modify the geometry optimally to restore standard working gaits for patients that have issues on their hip. And there is a company that is actually using these techniques to try to design improved teeth retainers that are applying controlled forces on the teeth, which are less painful than the one that currently exists. So this was just an overview of applications. And now back to the actual technique. So what I would like to tell you today is about this different formulation for contacting elastodynamics, which is, again, designed to be robust. That was the main reason to do it this way. One of the key ingredients, which is a new geometric contact potential, and then talking about the line search, which is a very special aspect of this. So the first thing, it's a few years that we are working on this. The first paper was in 2020. This is probably the first paper to look at if you are completely unfamiliar with this type of methods, but there have been many follow-ups. So just quick overview. In classical contact mechanics, the more common way to handle the resolution of contact, common sense of number of papers that are using this approach, is to try to take a step and add some sort of constraints that you're going to enforce using some numerical methods to resolve the intersection that might appear. The challenge with all of this is that as soon as you allow any constraint to be violated, it's very, very hard to have any formal guarantee that you're going to be able to satisfy them all. In particular, I'm not talking about satisfying them up to numerical precision. I'm talking about satisfying them exactly. So I want no collision at all, including numerical rounding. This is very, very hard. So this is an example of an existing solver. This is Chrono. Here, depending on the parameter that you pick for the time step, you can go from stable to falling down to intersection in the middle, which is a very unintuitive behavior. More systematically, so here are every column is a different method. Some are different gap functions. This group is using SQP, this other group is using quadratic programming with nonlinear constraints, and every row is an experiment. And you see on the left how the scenes look like. And by tuning parameters, you can get most of these methods to produce reasonable result, which is green, but sometimes they have intersections, sometimes they fail, and so on. So there is a much, much larger study on the paper, if you're curious about this. but we couldn't find any method that reliably can solve this no matter what parameters you pick. So what we are trying to do is to get to a point where we have guaranteed no intersection, guaranteed positive volume, and differentiable. How do we proceed? So an obvious way to proceed is a typical method using in structural mechanics, which is let's do explicit time integration and let's solve the contacts one at a time. This is very robust, but it's completely unreasonable in terms of runtime if you have many contacts, because every contact is going to shorten your time step. You end up taking tiny steps. So we propose something else, which guarantees no intersection, and it allows you to take large time step by using an interior point optimization approach with a twist. So the basic formulation is not new. It's something that I think most of you are going to be already aware with. It's a very old idea, but I'm just going to rederive it in case, quickly go over it in case no one saw this before. So let's just take Newton's equation of motion. We take an implicit time integrator, for example, implicit Euler, but this can work with arbitrary order BDF. And you get a system of equations. And then usually you solve this system of equations. If you have contact, these are additional constraints, but let's leave contact away for a second. You have a system of equations to solve. Now, solving a system of equation, if the system is non-linear, it's very hard. You might not be able to find a solution. And so there was a reformulation. It was very nicely written in this paper from Kane in 2000, but it's coming from a few years before, where you can actually rewrite a time integration as minimization of a potential. So these two are actually equivalent. So if you minimize this potential and if you find a global minimizer, this is going to be a solution of the system of equation above. And so at a first look, this might seem similar, but there are big advantages in going for this second approach. The advantage is that this is now an unconstrained minimization. And so, and in the paper is called incremental potential in this paper here. So that's why we call this method incremental potential contact. So what you can do here is now you have a term that allows you to minimizing E, it's accounting for inertia and elasticity. And you can now introduce your contact forces as the gradient of another potential, which we call the contact potential, which is defined in such a way that it diverges when two objects are exactly in contact. There is also another discussion here that you can approximate friction using a lagged approach and write it in some potential form, but I would prefer to leave this out because it's a long discussion on its own. I'll be happy to discuss this separately if you're curious about this, but for now, let's ignore friction and let's just focus on E and B. So when you have it in this form, now taking a step in time reduces to using Newton's method to minimize an unconstrained energy. So the idea here is that we are going to start from a point that has no intersection. The initial state should be intersection free. And then we are going to ensure that we stay in the feasible region by doing the following. We are going to use Newton's method. And then in the line search, we are going to ensure that we never violate the constraints. So note that the line search is crucial here because the potential, and especially this term here, the barrier, is definitely not linear or quadratic. So if you use Newton's method, we are going to move in a direction which is a quadratic approximation of our potential. So it's totally possible that this direction will eventually point to some place where we are violating constraints or the energy goes up, right? So, okay, but how does this help? How are we going to implement anything that works in this way without floating point? So the big intuition here and the core idea is that it actually does not matter what direction you pick for Newton, as long as in the line search, you do the checks exactly. So what we're going to do here is use standard floating point arithmetic to compute the Newton descent direction. If that one is problematic, we are going to go down to gradient descent and a lot of other robust ways to get a good direction. But then in the actual line search, we do not use floating point. Here, we do exact checks. And for an interesting coincidence, it turns out that this problem of validating no intersection and positivity of elements on a linear trajectory, which is what you get inside Newton, can be done extremely efficiently. So you can do it exactly. You do not need strange number types. You can do everything internally in floating point, but you can prove that this is conservative and guarantee that it's not going to create problems. So at the end of this, you get an algorithm which is very simple. It's standard Newton on a potential that minimizes a scalar potential. Catastrophic failures cannot happen because the line search will never allow you to violate these constraints. The thing that can happen is that it's going to take a long time to actually find a minimizer there. But I think this is a better failure than having something crashing or creating intersection or inverted elements and so on. So one advantage of these that I'm going to briefly mention is that since the only thing you are doing is minimizing a potential, now suddenly you also know how you want to change your discretization. You want to change your discretization if and only if you get a better value for your potential. So this also gives you a very natural way of refining your mesh, which is aware to contact, elasticity, friction, and whatever other term you have in there. Okay, so the key ingredient here are two. One is how do we define the potential and how do we define the line search. So for the potential, I'm going to very, very briefly go over this paper that has been published last summer. What we are trying to define is a potential that essentially measures how close objects are. And there is a large literature in contact mechanics, in graphics, in scientific computing on how to define these. But the large majority of the focus is on defining potential between different surfaces. Here, we want to have a potential that works between different surfaces, but we also want a potential that works for self-intersection, so a surface with itself. There is a huge variety of them. Some of them are purely discrete, some are purely continuum. There is a long list that has been proposed. But unfortunately, what we really struggle with is how to deal with self-intersections. Because in the literature, most of the literature, what it does, the problem is that if you have a point here, and you need to have a way to distinguish if there is an actual surface, for example, on top, which is going to touch this point, or if there are points close to it, but belonging to the same surface, right? So how do you distinguish these? There are a bunch of approaches. The two more common ones are to either ignore some part of your discretization around it, like a one ring. But as you can imagine, this leads to incountable trouble in trying to prove anything or showing convergence and so on. The other more common option is to try to use normals to distinguish if it's itself or another surface. The problem with normals is that they are not continuous, and so you deal with trouble if your surface is not C1 or C2, which in my case, they are always C0. And this is a real problem. So if you're not careful, you can get strange things like these, where just because the mesh is finer in a certain region, you get ghost forces starting to appear and the material trying to pull apart, which makes no sense. So what are we trying to do? So we're trying to define a potential, which is finite if the surfaces are not in contact and if the surfaces are not self-intersecting. It's infinite if there is a self-intersection or if two surfaces touch. It should have no forces at the rest shape or under rigid deformation. Ideally, it should be local. This is not strictly needed for the theory, but it's absolutely needed in practice because otherwise it becomes impractical to use for any large-scale simulation. And finally, we want this potential to be at least C1. Ideally piecewise C2, so that we can use Newton to optimize it. And the last piece, which is the thing that is less present in the literature, is that we do not want these properties to hold on a smooth surface or in the limit of refinement of a discrete one. We want all these properties to hold for the mesh that you are given, because that's the one that we're going to actually use for simulation. And so we started looking at the literature, and unfortunately, we could not find any existing papers that actually satisfies these properties in the discrete case, all of them at the same time. And in particular, there is this very large table, I'll just leave it here for a little bit, where we really try to dig into the entire literature on contact mechanics to try to figure out if this has been done before or we could use something that it's already there. But unfortunately, for various reasons that are described in a long document that is attached to this paper, we could not use any of these existing proposals. So we ended up re-deriving from scratch continuous potential, which allows for a discretization that satisfies all of these properties. And the sort of key idea, the construction is quite involved, but the key idea is simple, is that if you take a point and you want to evaluate the potential at this point, what you really care about is what is the distance to local minima of the distance function to any other surface or itself. And you can then filter these. The natural way to filter these is to use normals, which are well defined in the continuous case, but you can actually have an equivalent definition in the discrete case by using tangent instead, and you can have like multiple tangent at the same point, but you can still use these to identify these local minima. And so this leads to a very natural way of discretizing such a potential, and in the paper we prove that the properties that I listed before also hold in the discrete case. There is a catch. So first of all, like this is how this looks like. So as you kind of intuitively expect, if you're evaluating the potential as a point here, is sort of pushing away things that are close to it. And the catch here is that you unfortunately cannot use standard quadrature rules to integrate this potential. You need to use custom quadrature if you want to have all the properties that I listed before. Unfortunately, I cannot go into the details. I'm already running quite late, but I'll be very happy to discuss these separately. So the last piece, it's a line search. And the reason why I care about line search is, again, because I compute this descent direction in an approximate way, and I want to make sure that nothing is going to go wrong if I move in this direction. And anyhow, even I computed this exactly, I will need to know how far I can go before I hit something bad. So in the contact mechanics literature, this is usually called CCD, continuous collision detection. And the simpler one is to do point to triangle. So the statement is that you have a point moving in a linearized trajectory, you have a triangle moving in a linearized trajectory, and I want to know if they ever touch. And the question here is, how do I compute the largest t before an intersection happens? And I have an interesting story to share on this, because we spent quite some years trying to figure out a reliable way to do this, because we had failures from existing codes. And so what we sort of discovered is the following. In 1992, there was a fantastic paper from John Snyder called Interval Methods for Computer Graphics, something like this. It's a fantastic paper where they introduced a method that casts this problem as, let's find roots of a system of polynomial equations where a parameterized time here is t, which parameterizes these linear trajectories, and u and v are the barycentric coordinates of a point in a triangle. And the question is there any case where the point is inside the triangle? And he was doing this using a subdivision technique, which is guaranteed to work. As far as I know, this paper has never been used, and instead a more modern approach took over in both in graphics and in mechanical engineering, which is to use a univariate formulation where you first check if the point and the triangle are on the same plane, and then after this happens, you check if the point is inside the triangle. This is way more efficient because now you have a univariate polynomial. It's much easier to find roots, and then you do a simple check to see if a point is inside or not. It turns out that this is a really bad idea because there are many degenerate cases. So for example, if the point and the triangle all move in the same trajectory, you get infinite roots for this polynomial here. And so you cannot really know how to check if a point is inside or not. And so in the literature, there is a long enumeration of corner cases to try to get out of these. And our discovery is that it's very hard to do. So we took like millions of queries. For each one of these, we computed an algebraic solution using Mathematica. This is completely impractical. It takes like a few seconds per query, but this was only to get some ground truth we could actually check all the algorithms against. And what we discovered is the following. So all the methods that use the univariate formulation miss collisions. So we have counterexamples where we can show that there are actual collisions happening and they don't catch them. The only exception is this recent TCCD, which actually has massive numerical tolerances, and so it produces millions of false positive, like detects collision when there are none. And curiously, the only method that works for real correctly is this old paper from 1992, which is these two here, two variants. The problem is that it's extremely slow, so that's why people did not use it, probably. I'm going to discuss later an approach for getting same reliability, but considerably faster performance and same guarantees. The second thing I wanted to very briefly touch is positivity of elements, which is particularly relevant for elasticity, because at the end of the day, it's usually there is contact simulation with elasticity, and if elasticity part breaks, then the whole thing breaks down. So just to clarify what I mean, so every element usually has a geometric map from reference configuration, from the reference element to the current mesh element. And then if we do elasticity, usually we have some basis where we represent displacement. And so what we really care about is that the composition of a geometric map and displacement must be injective, right? So this is usually tested as we want the determinant of a Jacobian of this combined map to be positive, and in most codes, this is tested on quadrature points. However, testing on quadrature point does not give you the correct solution, because it could be that it's positive on the quadrature point, but it's negative inside, in some other spot. And we actually tried this, and we took simulations from a bunch of different places with nonlinear elasticity, and what we found is that all of them actually have inversion that are not caught by testing on quadrature points. And what is even more interesting, and it's something that I could not find anywhere in the finite element literature, there is literally only one paper that mentioned this that I could find, is that even this is really not enough, because you could have a situation where before you take your step, the element is valid. After you take your step, the element is still valid, but it flips in the middle. And this is easy to do for high order element. It's actually possible to do it for linear elements too, which is a little bit more surprising. And what I think it's crucial here is that if you have a simulation where in some part of your trajectory you have random inversions, I think it's very hard to trust that this is actually predictive. It's breaking one of the big assumptions that you make at the beginning, that your geometric map should be injected. So I don't have the time to show you how to derive these, but you can probably trust me that since everything here is polynomial, you can also recast these similarly to before as a root finding problem on a system of polynomial equations. So finding inversion is very, very similar to finding contact in the previous example I showed. And so there are many problems of this type, and we came up with an approach where you can specify at a high level what is your system of equations, what roots are you trying to find, and we have a method that uses intervals. I'm going to say what they are in a second if you're not familiar with it, but uses a lot of recent techniques that were developed in geometry processing for generating an algorithm which is provably correct with a proof of correctness that independently from numerical rounding, you're going to get a conservative proof, and that it's also efficient at the same time. And this can be used for fully automating nonlinear CCD between arbitrary shapes, the arbitrary element type. You can do intersections between arbitrary patches. Of course, like this is not going to give you the exact intersection. It's going to approximate it with a set of intervals. So it's not a replacement for cut. It's just a convenient way to create predicates that can be used in the line search. And the other thing that I'm really happy with is that it allows us to have ways to do checks for inversion of elements that works for any finite element type, any order that you want. You just change one line in the script here and you get an algorithm which is probably correct for doing this. The sort of core principle, it's a very old idea, and it's the idea of constructing range functions, or they're also called inclusion functions, depending in which field you look at them. So the idea is that if you have a function, here is g, this orange one, inclusion function for g, which is called ig here, is a function that takes as input an interval on the domain, here it's between 0 and 1, and produces an interval on the codomain, this green bar here. And for a interval function, sorry, for a functions to be an inclusion function of g, what must happen is that the output interval must contain all the possible values of a function in the input interval. Okay, so in a sense, it's estimating what's the worst that can happen in that region. So if you have such a way, so if you have an automated way of taking g and producing an inclusion function for g, which is conservative, meaning that even if there is some numerical rounding, g is a little bit larger and you catch it, then you can very easily search for roots. What you can do is you check if your green interval intersects 0. If it does, you split your input interval into two, I1 and I2, and you do it again. And you continue to repeat these until you are successfully all on top or all on the bottom, and you can really make a call if there is a root or not. Or you run out of precision and you're happy with, 10 digits of precision, and then you stop subdividing because that's enough for you, and you get a conservative answer up to 10 digits of precision. So more precisely, this inclusion function is to have two properties. So they need to be conservative and they need to be convergent, meaning that if you split the input interval, you get a sufficient reduction in the size of the interval in the codomain. And so there has been a lot of development in geometry processing on how to compute this. And in this paper, we propose a method for doing this construction automatically, and more importantly, to create a method that produces inclusion functions that are guaranteed to have these two properties in floating point. So I think the details are very, very technical, but the takeaway here is that if you ever care about doing root finding, or you need some of these predicates for checking for collision or validity, I would strongly encourage you to take a look at this, because it was constructed. We work on this project because I was really frustrated by doing this by hand all the time and getting it slightly wrong. And I think this is a very reasonable way to do it. So in terms of limitations, so the method is slow. What I just proposed is pretty slow. It requires a direct solver. One fantastic paper that just appeared recently is this Petrides 2026. Mike Puzo is one of the authors, and I think he's at the conference. It's a fantastic approach that has a real chance of allowing us to move from direct solver to iterative solvers. And I really hope that this is going to be eventually possible, because this is the only way to get these sort of approaches to be scalable to large problems and HPC. Another thing that I'm really annoyed about is that our proofs of correctness rely on the compiler executing the floating point operation in the correct order. And unfortunately, sometimes compiler update break these, which is very, very annoying to figure out when it happens. And then the last piece is that a formal analysis of convergence to a discontinuous contact model is still ongoing. There are experiments that show that it's very likely to be the case, but we don't have anything formal yet. Everything that I presented today is open source and on my website, both for mesh generation, for collision handling, for finding elements, and the source file for the scenes that you saw in here. It's all available on these websites. So to conclude, I hope that this different take has been interesting, that while it has been developed on the graphic side, hopefully it's going to be also stimulate work on on engineering side and in the contact community. I think it's a bit contrived, but it's the only way we could find to actually have these strong guarantees on successfully taking steps and ensuring no constraints violation. And you can do a lot of fun things, since this is one of my favorite, where we have this funnel, there is this dolphin, we have one point being pulled through, and after a very long suffering, this poor thing actually makes it through. So that's it for my talk. Wanted to thank the funding agency, NSF, Adobe, Autodesk, AMD, and Topology, the Sloan Foundation, and NIH for supporting all of this. And I would love to answer any question. I'm also going to be super happy to discuss separately with any of you. Just send me an email. We'll find the time. It's really a pity that I couldn't be there, but I hope there are going to be possibilities to connect remotely in any case. Thank you so much for your attention.
So thank you, Daniele, for the very impressive presentation. So while our helpers prepare for the next session, we open the room for questions. So who wants to start? So in case I'll break the ice. So you said that somehow there is some kind of performance bottleneck that makes the simulations last maybe a day or a week. And can you identify clearly what that is?
Right. So, I mean, it depends on the scene. So static scenes run into minutes usually, but whenever you have like a long sequence with thousands of time steps, then minutes easily become hours. The bottleneck is really that we need to use a direct solver because the system that we get from these are badly conditioned. And it's not easy to precondition them. So again, like this Petrides paper is the first preconditioner that is very effective at dealing with these problems. But before this, there was really no clear answer. The other thing is that the cost depends on how difficult is the scene. So the more contacts you have, the more these will take. So the timings are in paper, but overall, like I would love if we could be faster. In graphics, there has been a lot of variants of these approaches where they guarantees and get rid of a high accuracy of these methods to go for faster performance, and they even managed to push it to real time. But unfortunately, many of these drop the line search or use low accuracy linear solvers and do not get reliable and accurate results anymore. But so that's the current state of things. They are not like dramatically slower than things that are implemented in pure floating point. Maybe like the slowdown compared to other contact approaches, what we report in the paper is maybe like 3 times slower, 2-3 times slower, but still very far from real time.
Okay, thank you. There is a question from Mike. If you don't hear it, I will repeat it. So,
thanks for the presentation. I really appreciate what you guys do. I do have a question. If I have a stack of bodies that are, start out in contact, since you have a variable portion, will they, if they have a zero gap between them, will they automatically have a force between them? Something, or actually the variable below, right? Well, say I have my iPhone. My iPhone's got all parts basically, touching, at time zero. Would you automatically develop some sort of repulsion?
Daniele, were you able to hear it, the question?
Yeah, no, I was not able to hear it, unfortunately.
Okay, so the question was, if you start with a situation where the two bodies are already in contact, right? So it means zero gap, right?
Yeah, you get a repulsion.
So you get a repulsion.
Because of the variable.
Because of the
So unfortunately, no. So if the two surfaces are exactly at zero distance, we cannot optimize this because the potential is already infinity from the beginning, and the gradients are infinity too. So the assumption here is that the initial configuration cannot be in contact. So it doesn't matter. It can be like a very small gap between the two, but it cannot be exactly in contact. And so exactly because as you pointed out, this is very typical. This does happen. I'm going to share something else. So we have this recent paper here, this one, where we look at this problem of if you have surfaces that are very close by, can you separate them by adding some offset? And we have this paper where we show a construction for offset, which is similarly reliable. So it doesn't matter how complex the geometry is, you can always do it. And so what we currently do is that we use this approach to introduce a tiny separation in the beginning so that you can, then it's possible to use this sort of approaches.
Okay.
In general, like the overall idea is that we do not want the constraints to be violated in the beginning, because the entire argument and the entire reason our approach is so reliable is because it's easy to check if you violate a constraint, if you're in a situation in which it's not violated, but I do not know how to do the other way around. If it's already violated, having a method that guarantees that you can project out, that you can project back to the constraint is something that I don't know how to do.
Thank you.
Okay, so Mike says thanks. So I invite the participant to contact Daniele for further questions. So thank you again, Daniele, for a very interesting presentation.
Thank you, everyone.
So we see each other on the stream.
Yes. Bye. Bye-bye.